Hello and welcome to GeoProven, the Earth and Environmental Education Center of Provenance Geosciences in support of carbon negative water and energy. I'm Dr. John Hoaglund. Hello and welcome. My name is John Hoaglund. I am a hydrogeologist, that is a geologist who works in water, groundwater specifically, and I'm going to present today on what's in my water. Common question that I get from people all the time: what's in my water? It's usually because they're concerned about possible contamination in the water. And then a lot of times that gets to a curious question: where does my water come from? The two questions are related, and so I decided to combine a discussion of both in this talk. What's in my water is related to where does my water come from. But what's normally in water? And this will be a list. Major ions. Major ions are the common minerals that are found, what the people call minerals anyway. They're basically salts from rock-forming minerals that get dissolved into the water. Things like sodium, potassium, calcium, magnesium, sulfate, and chloride. They comprise 99% of the water chemistry, so they're pretty important. Minor ions, these are also minerals, but they tend to be derived from oxides and sulfides in the rocks, a little less abundant. They contribute things like iron and manganese. Trace ions, they're also salts from oxides and sulfides, but they tend to be even less abundant. There's sediment, which is measured as turbidity. There's organic matter, including weak acids, particularly organic acids from the decay of plant material. Dissolved oxygen, some gases and oxygen and carbon dioxide as well will dissolve in water. And there's certainly life that needs to be contended with, particularly with surface water, things like protists, bacteria, and viruses. And there's also an energy investment in water. I'll talk about that more, but it's important to consider that fresh water is energetically expensive. Taking a look at major ions, these are the cations. They're group 1A on the periodic table and 2A on the periodic table. That's the alkali and alkali earth metals. The 1As are sodium and potassium. Sodium, as the sodium chloride salt, is fairly common, but it also comes from clays and potassium feldspars. Same with potassium, comes from potassium feldspars and a few other very common rock-forming minerals. The group 2A, the alkaline earth metals, are calcium 2 plus and magnesium 2 plus. Those are the most common and that are dissolved in water. The anions, bicarbonate results from dissolving CO2 in the water. If you neutralize, it forms carbonic acid. If you neutralize the acid, you'll be left with bicarbonate, and that can build up in waters. And those waters are considered to be highly buffered because the bicarbonate can neutralize acid. Chloride, again, sodium chloride, a common salt. Chloride comes from rare minerals. And sulfate. Again, the major ions comprise 98% of the natural water chemistry. And based on the composition of these relative amounts of sodium, potassium, calcium, magnesium, as well as the relative amounts of bicarbonate, chloride, and sulfate, we can come up with water types. Water has a characteristic chemistry pretty much based on where it's been. And we can use that in the field to determine where different water masses are and where they're coming from. We can define different regions, and particularly in groundwater, where the water may have been sourced. A little more about the water types. They're named by the most major cation and the most major anion. For an example, you could have a calcium bicarbonate water or a sodium sulfate water. The groundwater reflects the local geology. As the groundwater moves through the local bedrock, it tends to pick up the chemistry related to those rocks, except where the water has been imported and put into the groundwater, and that's very common in Southern California, as we'll see later in this presentation. If it's allowed to move naturally through the aquifers, it'll evolve to a relative composition of seawater, which I find interesting. The water types can have different properties and different physiological effects as a result of this chemistry. First of all, we tend to put artificial carbonation in drinks, fizzy mineral waters, to mimic bicarbonate waters, which are the most common popular mineral waters. The bicarbonated water will buffer acid, and when it does that, it releases CO2. And so that's what we see in the natural carbonated waters, and so we tend to imitate that in our soda pops. Of course, artificial carbonation also mimics the yeast fermentation in beer. Calcium and magnesium waters are called hard. It tends to be that the calcium and magnesium will combine with carbonate actually and form kind of a scaling on plumbing and fixtures, and so people tend to try to treat that out of the water. Water softening is designed to remove calcium and magnesium and replace it with sodium and potassium so that the waters aren't quite so hard. But people with hypertension, sodium sensitivity shouldn't drink softened water. So there's an example of a physiological effect depending on whether calcium and magnesium is more major in the water or whether sodium is more major in the water. Magnesium waters are known to be good for dairy production, for instance. So if the soils are high in magnesium and the water is high in magnesium, the cows will produce more milk. And this is maybe too much information, but sodium sulfate waters, which exist naturally, have laxative qualities. One question that I'm asked a lot is, why does my water smell bad at the tap? Or another way of putting it is, I smell rotten eggs at my tap. Is my water contaminated? Usually no. What's going on is sulfate, one of the major ions in water, is being reduced in the plumbing. Sulfate, SO4, is an oxidized form of sulfate. When there's less oxygen in the water and you have bacteria working on it in what's called an anoxic, oxygen deficient environment, the bacteria will break down sulfate into sulfide. So first it consumes all the dissolved oxygen in the water, and then it starts to work on sulfide, or sulfate rather, and turning it into sulfide. So we have SO4 going to H2S, and it's the H2S that you smell. And it smells like rotten eggs. It's a harmless thing, but particularly with waters with high sulfate, you may notice a rotten egg smell at the tap if you haven't run the water. Usually if you run the water for a long enough period of time, the smell goes away because you're getting more fresh water into the plumbing. The minor ions that I mentioned iron and manganese. There's also boron, fluorine, and nitrate. Iron and manganese tend to come from oxides. Some of the iron comes from sulfides, which are minerals in the rocks. Boron have variable amounts. It tends to be associated with coal. We get a lot of boron in fly ash deposits, which are left over from coal burning. Fluorine and nitrate. Nitrate will come from, might be raised in certain areas due to fertilizer use. Nitrate will form from ammonia fertilizer, or urea from manure fertilizer will go to nitrate, and that's a nutrient that plants take up, but in abundance it tends to cause problems with excess plant growth and biotic growth in the waterways. We call that eutrophication. So in some areas, particularly agricultural areas, the nitrate levels might be up. And as for the trace ions, they generally, most of these that I think of will come from a sulfide, and you can tell that they're things that we don't really think of very often. The one on the left, aluminum, is more common in common rock-forming minerals, but it's fairly insoluble and doesn't end up in the water much. The ones that I marked in red are the ones that we tend to hear more often about. They tend to be the most common heavy metals that we end up getting in water, not the music type, the heavy metal ions. AS is arsenic, CD is cadmium, CR is chromium. The chromium levels can sometimes be raised due to industry when chrome plating was involved in making metals and metal finishing. Lead can come from plumbing. In old plumbing systems, they use lead for solder. Sometimes even lead pipe still exists. And the lead can be mobilized if the water is overly acidic. That happened recently in Flint, Michigan. Basically, more acidic waters, pH less than 7. Those waters tend to dissolve or at least mobilize metals in solution, keep them dissolved in solution, and so lead from the pipe gets leached from the pipe and into the plumbing. And then the other one, mercury. It's been a problem with paper production and other transformers and other sources of mercury. And selenium. Those tend to be the ones that we hear about. That ends part 1 of the presentation, part 1 on ions. Tune in to part 2 where we discuss total dissolved solids and biological considerations in the water.